effective span, and that effective span was, you can check the values, 3.15 meter. Then we have calculated ultimate dead load, and the value of that dead load is 6 kilonewton per meter. And then we have calculated live load, and the value of live load is 4.5 kilonewton per meter. Okay, so now what the next calculation is of bending moment. Now we are going to calculate the bending moment. Now where we are going to calculate the bending moment, that is most important. Okay. So see, to calculate the bending moment, there is clause in the IS clause which is given in the IS code. So we will move to that clause first, and then we will calculate the bending moment. Okay. So okay. So are you able to see the screen? IS code. Now here you can see this is the bending moment coefficients. Okay, table number 12. Page number it is 36. From this table we are going to calculate the bending moment coefficients. So here you can see this dead load or imposed load. Okay. So this is your dead load. Here it is imposed load means live load, it is given over here. Okay, so this is the dead load coefficient. This coefficient whatever given over here, it is the dead load coefficient, and this 1 by 10 is live load coefficient, and similarly this row is given. Okay, so now here you can see there are basically 1, 2, 3 and 4 columns are there. This is first, second, then third and fourth. At these 4 points we are going to calculate the bending moment in one way continuous slab. So first is the near middle of end span. Okay, then at the middle of interior span. First is the middle of end span, then second is the middle of interior span, then at support next to end support, and last one is at other interior supports. Okay, so I will explain you here only what does it mean. So now suppose this is our continuous slab, and the supports are, I will so I will not draw exact spans, but you can understand. 1, 2, 3, 4. Okay, so this is our continuous slab now. So now see what is the meaning of this. See here, first this is your end span. Okay, now you know what is end span and what is interior span. This span is your end span, this is also your end span. Okay, and these two spans are there, those are intermediate spans. Okay, or interior spans. So now here first we are going to calculate at the middle of end span. So middle of end span means this point. Okay, middle of end span means this point here. This is first number, I will write here first. Middle of end span. At this point we are going to calculate the bending moment. Then at the support next to end support. So this support, this is called as end support. This support is called as end support. This support is also called as end support. Okay, this support is also called as end support. So what they have told you, support next to end support. Okay, end support च्या नंतर येणारा support कुठला आहे हा. So here at this point, here our number 3. Support next to end support is this support. Here is number 3. Okay. Now second is the middle of interior span. Okay. Middle of interior span. So middle of interior span, these two spans are interior spans. Okay, so the middle of interior span means here at these points, So here second number column is there, I will use same number 2. Okay, those coefficients will be used there at that point. And last one is the at other interior support. So this is nothing but your interior support. This support is nothing but your interior support. Okay, so now here first at the middle of end support, what are the coefficients? For dead load it is 1 by 12, for live load it is 1 by 10. Okay, and how to calculate the moment they have mentioned over here. For you read that note which is given below. For obtaining the bending moment, the coefficient shall be multiplied by the design load and effective span. Okay, so we just need to multiply it by design load and effective span, total design load and effective span. So here in our case, what is our load? Our load is in kilonewton per meter. Okay, kilonewton per meter. Total design load means they take the load in kilonewton. So here what we do, total design load into effective span means in our case it is WL square. In our case it is WL square. Okay, because total design load, how it is find out? Total design load, so total design load is nothing but whatever load we have calculated in kilonewton per meter multiplied by meter multiplied by length, whatever this value is there, it is in kilonewton, and that is called as total design load. Okay, so without going much more into the details, I hope you understood that this is what is the whatever I am saying over here. So total design load. So simply you can remember over here that we have calculated UDL, that is the load in kilonewton per meter. Our dead load is also UDL. Our live load is also UDL. Okay. So that is why to calculate the bending moment we multiply this coefficient by the term WL square. Okay. So now we will move to the whiteboard. Okay. Here. Now bending moment. So first I will calculate the bending moment at end span. Okay. So first at middle at middle of end span. At middle of end span. So what are the coefficients? The coefficients for dead load is 1 by 12 and the coefficient for live load is 1 by 10. So our bending moment is my voice is not audible. My voice is audible.
Yes, sir. Audible.
So somebody is saying me that right from the start my voice is not audible. Audible, no? Right from the start my voice is audible.
Yes, sir. Audible.
Okay, so those who are having problem in the voice, please check your range. Maybe due to the range you are not getting it. Okay, so at the middle of end span. So at the middle of end span right now, just now I have shown you the coefficients. The coefficient for what we can say dead load it is 1 by 12 and the coefficient for live load is 1 by 10. Just we need to multiply those by the term WL square. Okay, so I will write here first formula. Bending moment is equal to here 1 by 12 into dead load. So WUD, I will use the notation just for your understanding. WU means ultimate load, D stands for dead load, into L effective square. We are going to take the effective span. So this is for dead load plus coefficient for live load is 1 by 10, okay, into ultimate live load, so WL, into L effective square. So when I put the values it will be more clear to you. So now bending moment. Bending moment is equal to, according to IS code, this coefficient is 1 by 12. multiplied by dead load. We have calculated dead load as 6 into L effective. L effective is 3.15 square, plus here it is 1 by 10 into live load 4.5 into L effective is again 3.15 square. So fastly calculate this value. So the bending moment is equal to, calculate now, 9.42 kilonewton meter. Okay, check the answer. Okay, 9.42 kilonewton meter. This is the bending moment at middle of end span. So whatever our end span is there, both the end span. Okay, at the center of those end span, this bending moment is there, 9.42. This is what is the meaning. Now second where we are going to calculate bending moment next to end support. Okay, bending moment next to end support. So what are the coefficients for bending moment next to end support? So the bending moment is equal to, okay, so we will see those coefficients. I don't remember right now what are the coefficients. Okay, so now if you see the coefficients, what are the coefficients? Coefficient is, this is next to end support. So the coefficient is minus 1 by 10. This is for dead load coefficient. Minus 1 by 9. This is the live load coefficient. Right now we have taken 1 by 12. This is for dead load. Dead load means what? We have used the notation WUD. And here this is for live load. Live load means WUL. Okay. And similarly, these two coefficients are also there. Okay. Now just see this, so that there will not be any need to open it again and again. IS code. So now this is minus 1 by 10 minus 1 by 9, where next to end support. Okay. So now we will take those coefficients. So our coefficients are minus 1 by 10 into, now I will directly put the value. Minus 1 by 10 is for dead load. So dead load is 6 into our effective span 3.15 square, plus again minus 1 by 9 is the coefficient for live load. Our live load is 4.5 into 3.15 square. Do the calculation. Let me know the value of bending moment. Okay, so 10.91 kilonewton meter. This is the bending moment. Okay. Third point, where we are going to calculate it now. So we are going to calculate it at interior span. Okay. So middle of interior span. Middle of interior span. So the bending moment is equal to, what are the coefficients for middle of interior span? It is 1 by 16 and 1 by 12. Okay, so 1 by 16 into 6, that is our dead load, 3.15 square, plus 1 by 12 into live load into 3.15 square. Solve it. Bending moment is equal to. So till now I will see the next coefficients. So 1 by 16, 1 by 12, it is for interior span, and at interior supports minus 1 by 12 minus 1 by 9. What is the answer? This value is minus, no? 7.44. Okay, so this bending moment is 7.44 kilonewton meter. And last, where we are going to calculate at interior support, at interior support. So the bending moment is equal to, the coefficients are minus 1 by 12 for dead load and minus 1 by 9 for live load. Let me know the value. I think minus 9.92. How much it is? Minus 9.9. 9.9. Okay. So minus 9.92 kilonewton meter. So all these are the bending moments. Okay. So from all these values, we will choose the maximum value. Okay. In MODA, don't look at the sign plus minus. Okay. We want the maximum magnitude to check the depth. Why we are not looking at the sign? Because the sign is there for the sagging moment and hogging moment. If the bending moment is sagging at that point, then the coefficients are positive and therefore the sign is positive. And where the bending moment is hogging moment, at that point the coefficients are negative, and that is why the bending moment is negative. So we will look up for the maximum magnitude over here. So this value is 9.42, then this is 10.91, 7.44, 9.92. So your maximum value of bending moment is 10.91. So choose this value for our further calculation. Okay, now take the check for depth. So next step is check for depth. So to calculate the check for depth, equate the bending moment to moment of resistance. Okay, so here the maximum value is 10.91. So equating maximum bending moment to moment of resistance. So bending moment is maximum bending moment equal to MR. So what is the maximum bending moment? It is 10.91. So 10.91 into 10 to the power 6, which is equal to now M20 and Fe415 is given. So moment of resistance for Fe415 0.138 FCK B D required square or BD square. Here we can calculate the D required. Okay. So it is 10.91 into 10 to the power 6, which is equal to 0.138 into FCK 20 into B is 1000 into D required square. So D required is equal to. So how bending moment is equal to WL square comes? Have you joined late rule number 47? Because I have explained this in that IS code where we are taking the coefficients. So go to that table and read the note below. Below that table note is given. So please read that note carefully so you will understand from where this value comes WL square. Okay. So design load means W into L is the design load. Okay, and multiply it by span. So W into L again. So it will comes WL square. Okay, and it is one way continuous slab. Here uh, no formula is applicable like WAB by L, WL square by 8, WL square by 12. These formulas are not applicable. Because of continuation of the spans, the bending moment will get distributed. Okay, so now D required is 62.87. Okay, D required is 62.87 mm. Now what is D provided? What D we have provided? I forgot that value. What is our depth? I think 100 mm. What depth we have provided? Let me know. Please check the depth. 100 mm. Okay. So D required is less than our D provided, effective depth provided. We have provided 100 mm. Hence it is safe. This is safe. Required is 62.87 and we have provided 100. So it is safe. Okay. So after this, now we will go for steel calculation. So next step is steel calculation. Okay. So in the steel calculation, you know the formula for area of steel. So AST, that is area of steel, is equal to 0.5 FCK BD divided by Fy bracket 1 minus square root 1 minus 4.6 mu divided by FCK BD square. Now just put the values. Still I will tell you the values. 0.5 is constant, FCK is 20, B is 1000, effective depth is 100, Fy is 415. Then this 1 is constant, 4.6 is also constant, Mu. Now here you should put the maximum bending moment. Okay, if we see the values, we have got the bending moment 9.92, 7.44, 10.91 and 9.42. So we are going to design it for maximum bending moment so that it is automatically safe for all other bending moments. Okay, so the maximum bending moment is 10.91. So we will design it for that. So here AST is equal to zero point 0.5 into 20 into 1000 into D divided by 415. Here 1 minus under root 1 minus 4.6 into 10 point, it is 10 point, how much, 10.91 into 10 to the power 6 divided by FCK D, and D square is there. Okay, in examination many of times you forgot to make D square. So area of steel, what is it? Okay, 324.12 mm square. So this is the area of steel. Now consider 10 mm diameter bars. Okay, and calculate the number of bars first. So assume 10 mm dia bars. So number of bars. How to calculate the number of bars? So it is total area of steel divided by area of single bar. How many bars are required? 4.12. So we will round up this value to 5 numbers. 5 numbers of bars are required. Okay. So if we provide the 5 bars, each of diameter 10 mm, then what is the area of steel we are providing? AST provided, which is equal to 5 into 5 by 4 into 10 square. What is the value? 392. 0.69, okay, mm square. So now calculate the spacing. Calculate the spacing now as, okay. So firstly we will calculate the spacing. S is equal to, how do we calculate? Area of single bar, divided by AST provided, okay. So AST provided is 392.69 into width is 1000. What is the answer? It is 200 mm, center to center, okay. Second thing is spacing is equal to, now this is main steel, we have already seen this class, is equal to 3D, 3 into D, D is 100 mm, so it is 300 mm center to center. And the third case, spacing is equal to 300 mm center to center in no case, okay. To choose the minimum value of this, minimum value is 200, so we can write over here, provide 5 bars of 10 mm diameter about 200 mm center to center. So this is our reinforcement. After this we will calculate percentage of steel provided, percentage of steel provided, percentage of steel provided, so this is PT provided, we call this as PT provided, so which is equal to, formula for this is 100 AST upon BD, which is equal to 100 into AST, area of steel provided, is 392.69 divided by B is 1000 and D is 100. So it comes out to be 0.39%. Okay. So after the percentage of steel calculation, next is now distribution steel. Now this is one way slab. So in one way slab, you know that this is one way continuous slab. Name of the slab itself is the one way continuous slab. So in one way slab, you know that the main steel is provided only along the shorter direction, only in one direction. In another direction, we always provide the distribution steel. So now we will go for the calculation of distribution steel. Distribution steel. Okay. So the distribution steel is ASTD is equal to, it is Fe415 is given, so it is 0.12% of BD, which is equal to 0.12 into divided by 100 into B is 1000 into D is overall depth, it is 120. So it works out to be 144 mm square. So here we will assume 8 mm dia bars. So if we assume 8 mm diameter bars, then calculate the number of bars first. Number of bars is equal to AST divided by area of single bar. Single bar is of 8. So it is 2.8, which is nearly equal to 3 numbers. So ASTD provided. So instead of 2.8, we can't provide 2.8 number of bars. So 3 into 5 by 4 into 8 square is 150.78 mm square. Okay. So this is your distribution stick. Okay. Now what we will do next? We will calculate the spacing. Okay. And where the spacing is given, page number 46, clause number 26.3.3. Okay. So according to that clause, we will provide the spacing, and on the same page, clause for the spacing of main steel is also given. So you read it. Spacing S. Okay. So first, spacing is equal to, what is the spacing now? It is area of single bar divided by AST provided okay 150.78 multiplied by 1000 width. Let me know the answer. It is 333.34 mm. So we will round up this value to we will round up this value to 330 mm. After that again spacing S is equal to, it is 5D, 5 into D is 120, which is 600, sorry D is not 120, it is 100, which is 500 mm center to center. And the third thing is spacing is equal to, in no case it is 450 mm. So choose the minimum value of above. Minimum value is 330. So you can write here, provide whatever your 3-4 bars of 8 mm diameter about 330 mm center to center. Okay. So this is the design of steel. After designing, we need to take the check. So we have to take the check for shear, check for deflection, and then check for development level. So first we will take check for shear. So check for shear. For that we have to go to table number 13. Okay. From where we are going to calculate this? that is table number 13, clause number 22.5.2, page 36. Okay, so now we will move to this first. So here see, you can see here after bending moment, shear force. So this table which is given over here, it represents, so here in this table now, again the coefficients are given. Okay, so these coefficients we are going to use to calculate the shear force. Okay, so while designing, while we are taking the check for shear force, we should consider the maximum shear force. Okay, now we are having two end supports, then three interior supports. So out of which, where is the maximum shear force that we need to calculate? Okay, and how do we calculate that? With the help of these coefficients. Now see here. So at the end support. So again same thing is there. This is dead load and this is live load. So dead load and live load. So at end support, what are the coefficients? Zero point 0.4, 0.45. Okay. At support near to the end support. At support near to the end support, what are the coefficients? 0 0.6, 0.6. Okay. Then at other interior spans, 0.5, 0.6. Okay. So here I will tell you one shortcut. So the answer is 19.84 kilometer. Okay. So this is the answer for VU. So after the calculation of the maximum shear force, now we got the value of VU. We calculate the nominal shear stress. Okay, now we will calculate nominal shear stress. It is tau V is the notation, which is equal to VU upon BD. This is also given in IS code. I have already told you where it is given. 19.84 into 10 to the power 3 divided by BD. B is 1000 and B is 100. So therefore, tau V is the nominal shear stress. This shear stresses get developed in the one-way continuous slab. It is 0.198 Newton per mm square. That is megapascal. Newton per mm square means megapascal. I think you may know the conversion. 1 megapascal equals to 1 Newton per mm square. Okay. So tau V is 0.198 Newton per mm square. Okay. So now we need to calculate the permissible shear stress. Okay. So now our next step is calculation of permissible. This is the generated shear stress in the one-way slab. Now we want to calculate the permissible shear stress by IS code, the allowed shear stress. And to calculate the permissible shear stress, we required percentage of steel at the support. Okay, we required the percentage of steel at the support. So that percentage of steel at the support It is how much? It is 0.3%. So here percentage of steel, and suppose we have already calculated it, it is 0.39%. Okay, it is 0.39%. So therefore, now the tau c is equal to, we need to calculate the value. From where we are going to calculate the value? From table number 19, we will do the interpolation. So go to the IS code again. So these are the table number 13. 13. So we have to move to table number 19. So each number is, this is your table number 19. Okay. Now from this table, we are going to calculate the value of permissible shear stress, that is allowed shear stress. So here, so this is our percentage of steel, it is 0.39%. So 0.39% is comes between in these two values, here somewhere 0.39%. Grade of our concrete is M20. So for 0.25% it is 0.36, and for 0.5% it is 0.48. Okay, so do the interpolation and calculate the value. Okay, so for 20.25, how much it is? 0.36. Okay, and for 0.50 percentage of steel is 0.50, then value is 0.48, and we want the value for 0.39. How much? Do the interpolation and calculate the answer. Here your value of tau c will be 0.43 Newton per mm square as per my calculation. Okay, so now we will move to the whiteboard. Here tau c is equal to, or I will write something over here first. From table number 19, okay, we get table number 19 of IS 456 2000. You write the page number. Tau c is equal to 0.43 Newton per mm square. So now compare who is greater, who is less. So tau v is less than tau c. So the permissible shear stress is greater than the shear stress which is induced. So this is the generator shear stress in the slab, which is 0.19, and this is 0.43. So it is safe. So it is safe. So this is the check for shear. Next is the check for deflection. Check for deflection. I have told you, if your assumed percentage of steel is greater than your percentage of steel provided, then there is no need to take the deflection check. Okay. But here in our case, we have assumed 0.3 initially. Okay, 0.3 we have assumed. And what we have provided? We have provided 0.4, that is 0.39. Okay. So here we should take the check for deflection, because our assumed percentage of steel is not greater than our percentage of steel provided. That is the reason why we are going to take this deflection. Calculate this deflection. So again, to calculate the deflection, first we will go to figure number 4. Okay. So from that we will calculate the value of Fs first. Fs is equal to, it is 0.58 into Fy is 415 into area of steel provided. So first of all I will write the formula so that it will be easier for you. Fy into AST required divided by AST provided. Okay. So now we are having all the values. So we will just put the values over there. So Fs is equal to 0.58 into 415 into 324.18 divided by 392.69. So the value of Fs is works out to be 198.70. So we will take the nearly value as 190. So the percentage of steel provided, what is the percentage of steel which we have provided? It is 0.39%. Okay, so we will calculate the modification factor now. Therefore, modification factor MF is equal to, so now page number 35 or 36 something is there. Here. Okay. So now our line is 190 line. So I will mark this line first. This is the line 190. Because our 198 value is nearer to the 190 than 240. So we have taken this 190 value. Then after that, on x-axis you know that here is the percentage of steel. This is your percentage of steel. And on y-axis here the modification factor is there. Okay. So now your percentage of steel is 0.39%. So 0.39% is somewhere here. So if I draw the line from 0.9%, it will go 0.39%, it will go somewhere here. Okay. And then we will measure it from this point. If we measure it, then what is the value? This value you can see it is nearer to the 1.65. Okay, 1.65, 1.65 or 1.7. So this is the value of MF. Now we will again move over here. So the modification factor is 1.65. So now further, what we will do now, we will calculate the depth. So you know the formula, depth D is equal to effective depth is equal to span divided by 23 into modification factor, which is equal to 3150 divided by 23 into 1.65. It works out to be 83 mm. Okay. So D for deflection, depth for deflection, which is equal to 83 mm, is less than D, which is provided, which is equal to 100. Hence this is also safe. So this is also safe. And the last check is for development length. Okay. And the last check is for development length. Now here one thing you should consider while calculating the development length. Development length. So development length is always provided at the support. You see, development length is always provided at the end support. Okay, that is the most important thing. कुठेही डेव्हलपमेंट लेंथ देत नाही आपण. ओके, डेव्हलपमेंट लेंथ इज ऑलवेज गिवन at the end support. This is your view. Okay, now this support is your end support. This is your end support. For any other intermediate support, we won't provide the distribution of the development length. So now if I draw the diagram and if I draw the reinforcement details, it will be like this. You can see this bar now, it is not left alone over here. Some length of this bar is embedded into this bit. This is your development length, and development length is always at the end support. Okay. So now the formula for development length is LD is equal to phi sigma s upon 4 tau BD. Phi sigma s upon 4 tau BD. काय? अजून भरपूर अर्धा तास. Just 1 minute.
सेक्युलर आहे
कुठलं?
तर मग काय असेल
हां.
वगैरे
हां.
ठीक आहे. तर त्याच्यानुसार आपल्याला 3 तारखेपासून 15 तारखेपर्यंत त्या पोर्टलवरती मार्क भरायचे. ठीक आहे.
3 एप्रिल ते 15 एप्रिल.
हा, याचा अर्थ आपल्याला
आता
25 एप्रिल पर्यंत 25 एप्रिल ते 30 एप्रिलच्या दरम्यान ऍटलिस्ट बोलतो ऍटमॉस्ट आपल्या सेकंड इयरचा वायवा झाला पाहिजे. तोपर्यंत तुमचा सिलेबस होतोय का? कारण मला सेकंड इयरचा काही कल्पना
सिलेबसचा काही विषय नाही, आपण घ्यायचे व्हायला काय करा.
सीसीने एकदा विचारून
कळायलाच पाहिजे
कुठपर्यंत सिलेबस आला त्यांना टार्गेट द्या. कारण आयएससी सगळे
टार्गेट सगळ्याला तर किती एप्रिलचं
दिलेलं आहे का?
हा मग सगळ्यालाच 30 एप्रिलचं. बोला मॅडम. झालं का? नंतर बोलू आता आपण उरलेलं. 30 एप्रिल टार्गेट दिलेलं आहे त्यांना, बघू परत.
बोलूया महत्वाचं आहे.
So phi sigma s is now phi is 10 mm diameter into sigma is 0.87 into fy. Fy is 415. Okay. So divided by now tau bd. So 4 is constant. You know that for M20 concrete the value of tau bd is 1.2 and it is provided in tension reinforcement. So we have to increase this value by 1.6. So the development length, it's work out to be 470.11 mm. Sorry, 11 mm. This is your development length. Now we need to calculate the shear force. So shear force at support. हा so the shear force at support. झालं सगळं रेडी. संपलं काढतो. टाइम टेबल झाले तिन्ही डिव्हिजनचे रेडी. टेंटेटिव्ह माझ्याकडे व्हॉट्सअप वरती कागदावरती लिहून आलेलं आहे. कोण कोण कुठल्या कुठल्या दिवशी येणार ते तुम्हाला फॉरवर्ड करतो 1-2 मिनिट. नाही झाल्यावरती काढतो. तर डायरेक्ट मेल वरतीच टाकू ना सगळ्याला 20 टाकेल. एकदा तुम्हाला पाठवतो की एकच मिनिट. एकदा बघा परत काय अजून चेंज असलं तर, नाहीतर परत एकदा ऑर्डर केल्यावर. नाही मी टाकतो की ऑर्डर बिल्डर सगळं. फक्त एकदा हा फॅकल्टीचे नाव आहेत आणि वर डेज लिहिलेले आहेत. डेज म्हणजे वार, मंगळवार, बुधवार, सोमवार असं. हा होय ना. चालू व्हायला उशीर झालता. नाही नाही व्हॉट्सअपवर टाकले तुम्हाला. हा ओके. So shear force at support now we want to calculate. Here development length is at near support. So we want to calculate the value of shear force at support. So again we will go to the IS code. या सगळ्यांचीच असं डे वाईज ऑर्डर काढून द्यायची क्लास वाईज. मंडे SYTYB मंडे कोण कोण स्टाफ येणार. नंतर ट्यूजडे SYTYB कोण कोण स्टाफ येणार. थर्सडे कोण स्टाफ येणार आहेत काही नाही. कुठल्या क्लाससाठी आपण तुला लेक्चर आहे ना त्यांचं. बरं ठीक आहे. मग ह्याच्यातले कंबाईन सोमवार, मंगळवार, बुधवार टाकून देतो मी नाव. ठीक आहे. मग तेवढा एक टेबल तयार करून मेल करतो मी डायरेक्ट आता. टेबल करतो की डे वाईज. हा ठीक आहे चालतं. Okay, so now again development length is at the support, so we should calculate the shear force at support now. While designing the shear force or taking the check for shear force, we have calculated the shear force at where we have calculated the maximum value of shear force, and we got the maximum value of shear force. It is where it is at support next to end support. Okay, it is not at the end support, but development length it is always calculated at the end support. Okay, so see here. So now previously we have taken these values, these coefficients, and we have calculated the maximum shear force. But if you see, the maximum shear force is that support which is next to end support. So if your slab is continuous slab is like this. Okay, so this value 0.6 next to end support. So these are your end supports. So next to end supports means here these values are calculated. Okay, but now for development length, if we want to calculate the development length, so development length is always at the end support. Development length. Okay, are you getting my point? So now we want to calculate the shear force at end support. What is the shear force? So at end support, here you can see at end support these are the coefficients. Okay, this is the coefficient for dead load, this is the coefficient for live load. The coefficient is 0.4 and 0.45. Okay. So for dead load 0.4, for live load 0.45. So again we will calculate the shear force. So here shear force at support. So shear force at support, VU at support, it is 0.4 for what dead load into L plus it is 0.45 for live load into L. L means L effective. Huh? L means here L effective. So what is your shear force? It is 0.4 into load is 6 into span is 3.15 plus here it is 0.45 0.45 into 4.5 into 3.1. To calculate this, so we will get the value of shear force, is 0.4 into 6 into 3.5, 13.93. Okay, so see, we are getting the different values. So at support the shear force is 13.93, okay, kilonewton, and maximum shear force was 19 point something. Okay, so after the calculation of shear force at support, we will calculate the value of m1. M1 is equal to, you know that it is mu by 2. So mu is the maximum bending moment and it is 10.91 or something divided by 2. So what is the answer? 10.91 divided by 2. It is 5.45 kilonewton meter. Okay. Now last thing is L0. So you should take it as width of support divided by 2 minus clear cover. This is only used to 0. So now width of support, it is, if it is given in the problem, then it is okay. If it is not given in the problem, then you need to assume the width of support. So I will check it is given in the problem or not, width of support. So I think the width of support is not given. 150 mm support we have considered. Okay. So width of support is 150 divided by 2 minus clear cover. Clear cover is of 15 mm. So this comes out to be L0 is equal to 75 minus it is 60 m. So now after all these calculations, now calculate LD1. It is 1.3 into mu m1 into m1 by vu plus L0. So now calculate this value. So it is 1.3 into how much m1? M1 is 5.45 into 10 raised to 6 divided by vu. What is the shear force value we have calculated? 13.93. So it is 13.93 into 10 to the power 3 plus 60. So it is 568.61. 68.61 mm. So here your LD1 is greater than LD. So it is safe. So you can, or you can say your LD is less than LD1. So therefore it is safe. Okay. So now at the last, I will show you the reinforcement drawing. Okay, in the PPT you draw that drawing. So we will wind up the lecture here. You send your roll numbers into the chat box and simultaneously see this drawing. Where is that PPT? Okay. Now here you can see how the steel is provided. So this is the 8 mm bar about 130 mm center to center. So this is your main steel. So these are the 8 mm bars about 130 mm center to center. This is your main steel. No, this is your distribution steel. And the 10 mm bars about 250 mm center to center. This is your main steel. Okay. So now see the reinforcement details. In this way the steel is provided. So your main bar, first main bar, it will start from this point, then it will bend up to a distance of L by 7, then it will move continue, okay, up to this point. okay, up to the center of this first support. Then your second bar, or otherwise I will draw. See here, first bar, this will go like this, then it will bend and it will move further. Okay, then your second bar, it will start from this point, then this will bend and this bar will move forward like this. Okay, third bar, then third bar is you start from this point. Okay, part of it. Then it will bend and it will again move forward up to the center. Okay. Then fourth bar, it will start from this point, again it will bend and it will move up to this center. Next bar, on the next support, again it will start here, bend and it will move further, and this is the last bar, and in this way the reinforcement is continued. This is your main steel. Whatever we have shown over here, these are your main steel bars. So whatever is the main steel we have provided, those bars will move like this. Okay, and these small bars which are provided over here, dots, these are your distribution steel. This is your distribution steel what we have calculated. Okay, so these are your distribution steel bars. So this is the bent up distances L by 7 for this first bar. Then this second bar, which is start from this point, okay, from this point, and then it will bend. So from center, its distance should be L by 5. At a distance of L by 5 from the center line of the support, it bends like this. Okay. Same on this side also. From the center of the support at L by 5 distance. So this bar will bend over here up to the distance of L by 5, and same it is continued. This is continued here and this reinforcement is continued here. Okay. So this is the reinforcement details. Draw the diagram. I will wait till you draw the diagram. Okay, then I will close it. So to